大家好，我是张守成，我是 Stanford 大学的教授，也是清华大学的教授。这次呢，我正好和一位著名的物理学家Frank Wilczek 来到上海开会，所以我一直有个心愿，就是在做一系列的采访工作，真正跟世界上的最著名的第一流的科学家相互的交流，他们在交流过程当中，把他们自己学习科研的精神来传授给大家。Frank Wilczek 教授呢，他是一位非常著名的理论物理学家。他在做研究生的时候，他的科研工作是后来30年之后就得了诺奖。他是在做基本粒子物理的研究工作，但是他的兴趣却是非常广泛。就在物理的领域里面，他也涉及了不只是高能物理，还有天体物理，还有凝聚态物理。但是呢，他的兴趣更广，他还是写了很多的就是为给大众科普的书，那么他写了3本书，其中最近的一本书，就是我们今天采访的主要的题目，是叫 The Beautiful Question， 就是一个非常美丽的一个问题。So basically, I'm explaining that I'm interviewing a famous physicist. In your graduate work, you already made a major discovery, which eventually earned you the Nobel Prize. But you're also extremely broad within physics. You are interested in particle physics, where you made your original contribution, but then in astrophysics, but also in condensed matter physics, in quantum physics. But also even broader, you are interested in art, you are interested in philosophy. I am a passionate reader of your Wall Street Journal articles and your books, but also you write popular books to communicate science to the broader audience. So that's why we're conducting this interview today. So the book is about the beautiful question, 一个非常美丽的问题，就是我们在探索整个自然的一个最基本的规律时候，为什么在寻找最真的真理的时候，也会发现这个美。So basically the book conveys the idea why as we search for the ultimate truth, we always also find beauty at the same time. So my first question to you is that, Frank, you have written quite a number of books, popular books, communicating science to the broader audience. What motivated you to write this current book, The Beautiful Question?
Well, I feel as time goes on, I understand things more and more deeply, and in many ways also more and more simply. I try to understand, strip away more and more of the complexities, the accidents about the structure of the world, and get down to the deep lessons that our increasing knowledge has taught us. So, of course, many of those lessons are about facts of nature, but other lessons are about the kinds of questions that people have called philosophical or even theological.
Right, or metaphysical.
Or metaphysical, about what is truth, what is beauty, why is the world the way it is, what do we learn when we get down to the most basic description of nature, because now we're getting there. We really have an account of nature that's very compact, that's very well tested, that covers almost all phenomena that have been observed, and certainly gives us firm foundations for chemistry and engineering and ordinary life. Biology, presumably it's the laws that govern ourselves. So we can look and what is it, and why is it, and kind of think about why it's that way. We can also think about how we got there. We can compare what people were hoping for in their description of the world. I'm not sure I remember why, but for some reason I was revisiting some of the dreams of my childhood.
Tell us what were your dreams?
When I was, well, first of all, I mean the sort of pre-dreams were I was raised as in the Roman Catholic tradition, and I took it very seriously when I was a child. That the world was full of meaning, full of structure. But as I learned more about science, I realized that the stories couldn't be interpreted in a straightforward way, and had to be taken at best as metaphors, and sort of had a turning away. but I became very interested in the same. I still had a yearning for this kind of understanding that the world had deep messages, had deep meaning, and I went to my local library and looked around, and the books that really caught my attention were books especially by Bertrand Russell. Was a big early hero, and he wrote beautifully for one thing, so that I could understand, felt that I understood it.
Yeah, and you enjoyed reading.
I enjoyed very much reading. And one particular book that I read many times is called The History of Western Philosophy.
Right.
And in that book he talks a lot about, unusually for a philosophy book nowadays, he talked a lot about what the ancient Greeks thought.
Right.
And the ancient Greeks, in those times, there wasn't a division between science and philosophy.
Right.
People were asking...
Philosophy is simply the love of knowledge.
Yes, the love of wisdom is the meaning of the word, and people didn't break the endeavor into thinking about the logical structure of the world or the meaning of the world versus the facts of the world, of how it actually works. That kind of separation is much later. And but then reflecting on that much later, in the light of what I learned and discovered, I realized that the questions that they were asking and the answer, now that we know the answer has many things in common with what they were hoping for.
Right. That's remarkable.
Yes.
Yeah. 2,000 years ago, right?
2,000, almost 3,000 years ago. Well, 25. A little over 2,500 years ago. In particular, the Pythagorean school was a school of philosophy which was enormously influential. Drove a lot, indirectly inspired a lot of later history of philosophy, but their original concept was very mystical. They thought that the deep structure of the world is not appearances, which are very complicated, but somehow underlying it was numbers. Their very famous saying was, all things are numbers. And then that sort of got generalized to all things are concepts. All things are not just numbers, but sometimes shapes.
Yes.
The most ideal symmetric shapes. So for instance, Plato, was very much inspired by these ideas, made an atomic theory in which the basic building blocks of matter were things we call now the Platonic solids.
Yes, 5 of them.
There are 5 of them. There's the cube, the octahedron, the icosahedron, the tetrahedron, and the dodecahedron, the 12-sided calendar figure, and those are all there is, and that made an enormous impression because you could imagine many if the number were infinite, it wouldn't be suitable to get a compact description of the world. But there are only 5. And people at that time thought there were 5 elements. On sort of other grounds.
And there was a coincidence.
5 is very close to 4. It's not quite equal, but you could fudge the theory by having. What Plato in fact did was say that there are 4 atoms, but the dodecahedron is different. That's the shape of the whole universe. So genius can get away with these kinds of tricks and sleights of hand. So, of course, in detail, that theory is completely wrong. But in spirit, it struck me. It's kind of a revelation.
Struck you at the time when you were
when I was thinking about
child.
writing this book. Much later. Much later. When I knew
so you kind of revisited your own past.
Revisited my own past, exactly. Thinking about what I'd learned and what it all meant and how it related to the questions that originally inspired me.
Yeah.
And I realized that what people hoped for, at least some people, is what actually happened. In fact, happened to an extent and with a richness and depth that they could not have imagined.
Right, right.
Because they were kind of mystical. They didn't have the modern, one thing they didn't have is the modern concept that science should be rigorous and quantitative. And you have to make detailed comparisons between with the reality and experiment and your theories. And it's not enough to have theories that sort of look vaguely like the world and say the world is not good enough to be the home of our theories, which was the actual Platonic attitude was there's an ideal world which is different from ours. Ours is just a degraded copy. But now we insist that the actual world is the world of mathematical perfection, and the mathematical ideas that have proved to be necessary, but also adequate to describe the world, have a richness and depth that goes far beyond even the Platonic solids. The Platonic solids are very beautiful, but they use kind of, by modern standards, primitive ideas about geometry. The theories that actually describe the world work in spaces of higher dimension. They have
but yet
much
they have the
larger
key
degrees
concept of symmetry.
Symmetry, yes.
Symmetry. That is in common with
the symmetry, but in a very much heightened form, with as in much more symmetry and much more sophisticated.
And every time they're tested, they're actually verified by very detailed.
Well, that's the most amazing thing, right? And only really became possible, was only really in the 20th century, and particularly in the last part of the 20th century, that we used the principles of quantum theory plus this idea of very heightened symmetry to get a description of the world. And it works. You know? So you can do little squiggles on paper and calculations, and then it's a miracle. You take that and compare it to what people do with very detailed, careful experiments with measurements of thousands of collisions and what probability for different things happening when you have at very elaborate facilities with the high energy collisions which boil down the interactions to their absolute essence, stripping away and all the complexities of things that set in when things are moving slowly and interacting with each other in many times in complicated ways. When you get to the real essence, it's revealed to be, in a very concrete sense, simple and amazingly beautiful. That you could teach it to a computer with a program that's not astronomically long. You could define all the symbols, all the meaning of the equations, and just calculate. And that calculation would be like, it would give you a sort of map of the world. There would be things that emerge from this calculation that have all the properties of molecules interacting with each other, and they match. That map matches the behavior of the actual molecule.
So in the spirit of five Platonic solids, if I ask you to mention 5 triumphs that inspired by beauty and simplicity, we make a prediction that is confirmed by the real experiments in precision detail. What would you say?
Oh, golly. Listen, okay, so...
in the history of physics.
In the history of...
because some of them you were discussed by your book.
Yes.
Your book is very much a recounting of that history and that triumph.
Yes, some of the triumphs. Well, okay, so I guess I'll try to think about it kind of...
5.
Yes, I'll try. But I'll think about it chronologically. I think one of the most striking classical confirmations or verifications was Newton had a very specific law of gravity that he postulated that made very precise predictions about the motion of planets and so forth. And that was the first case, really, where this ideal of not being satisfied with a rough description, but having an absolutely a rigorous quantitative comparison of observation and calculation. And it was a triumph in many ways, but that meant that people took discrepancies very seriously. Even if they were minuscule, tiny discrepancies of where things should be, that accumulated over many years. And people noticed when they studied the position of the planet Uranus that it wasn't quite where it should be, that something seemed to be wrong. And one attitude would have been to say that, well, there's something wrong with the law of gravity. Another would have been the Platonic idea would be to say, well, you shouldn't really hope for absolute. You shouldn't really hope for absolute. Don't worry about it. But the attitude which proved fruitful was to say that no, the equations are too beautiful, too perfect to be wrong, and therefore we have to look to some thing in the world that's causing this effect. And two astronomers, mathematical astronomers, Leverrier and Adams, independently calculated that if there were a new planet in a certain place with a certain mass, it could account for this discrepancy. And so they could tell observers, look there, you'll find a planet, and they did. That's how Neptune was discovered.
So that's one, Newton's law of gravity.
That's one, Newton's law of gravity. I think, well, clearly another, maybe we should march through the interactions, okay? So coming to the middle of the 19th century, much had been discovered about electricity and magnetism. But Maxwell tried to put all this together into a consistent mathematical description that described all the experiments. And when he did that, he found that it didn't quite work. There was a contradiction. A mathematical contradiction. There was a kind of imbalance so that if you analyze things one way, they gave one answer. If you analyzed them another way, they gave another answer. So each was a kind of an extrapolation of known physical laws, but they gave, when they extrapolated, they gave a contradiction. And Maxwell, however, noticed that if he added a new effect, a little bit of a new effect, that he could fix this discrepancy. So this was a new effect that would have escaped observations, so it was consistent with what was known and would relieve the mathematical contradiction. So he proposed that new kind of effect occurs. The effect is that a changing magnetic field produces an electric field in a very precise way. So he proposed that, and then you could study the new system of equations, and the new system of equations had solutions which the old system didn't have, and those solutions included the possibility of having disturbances in space and time, electric and magnetic fields that kind of danced and reinforced each other and moved along. Maxwell was able to calculate that they would move along at the speed of light. And so Maxwell said, well, that must be light. That's what light is. And that's, to this day, that's our understanding of light. But there's much more. Because these disturbances are only light, only things we see, light in the ordinary sense, when they have a certain range of wavelengths. But the equations allow all wavelengths. So since then, people directly out of understanding Maxwell's equations and where they pointed, discovered ultraviolet light, infrared light, microwaves, radio waves, X-rays eventually. So all these things were in the equations that had been discovered purely by synthesizing experimental data, but also enforcing mathematical consistency at the end. So that's two.
But maybe we should just just one.
Well, then of course I should talk about my own work. So we had this problem in describing subnuclear forces that there seemed to be building blocks of protons called quarks that had a very powerful tendency to bind together, and you couldn't pull them apart. So many experiments suggested that there were these things inside protons, but they had never been observed as separate particles. They seemed to always hold together, stick into triples inside protons or in mesons. There'd be a quark and an antiquark. So this was a puzzle that, why do you have these, is it even sensible to have a kind of particle that actually can't escape? And the problem heightened when people took, by very sophisticated experiments, snapshots of what's inside a proton and found that indeed there are these particles that don't escape, but when they're inside the proton, they seem to hardly interact at all. So they have a very weak interaction when they're close together, but very strong if you try to pull them too far apart. So this is a very paradoxical kind of force. Most forces, when things get close together, the force between them intensifies. It doesn't get smaller. And it turns out that it's very difficult to reconcile that kind of force with other basic principles, with principles of quantum mechanics and relativity. That makes a very tight framework, and so it's very, very difficult to make forces with arbitrary properties, and this particular property was very challenging to try to build in. And so we had to guess, we had to look at what possible theories, what possible ideas could we have. Now, what guided us to the right equations were that C.N. Yang and Mills had produced, really by considerations mostly of mathematical elegance, a kind of theory that was had enormous symmetry properties and was consistent with relativity and quantum mechanics. But at the time they proposed it, they didn't have a concrete application that was successful. It was kind of free speculation about. Now that's a little oversimplification of history, but it's in spirit correct. They didn't know how to properly apply these equations. But it turned out that those equations, which were postulated on the basis of mathematical beauty and consistency, were just what we needed to get, when you worked it out, to get this crazy kind of force that gets weak at short distances and grows at long distances. So by studying the properties of that kind of equations and demanding that it match this very striking but qualitatively simple phenomena, we were led to a unique theory of the strong interaction called quantum chromodynamics, which is what got us a Nobel Prize, and also is the accepted theory, which has many beautiful features. And that was another thing that struck me when I came back to these ideas and thought about writing the book, is that we would never have been able to find those equations unless they were beautiful.
Right. That's a deep message. Right.
So so it was a gift. A gift from heaven. That nature works this way. If it didn't work that way, we would have a much harder time getting to a deeper understanding.
So, Frank, we're also extremely grateful you are coming here to China, and through this program, we're speaking to the aspired young scientists here. So, it is a very common and accepted concept that science is very useful. It helps the humanity, it can benefit the humanity, can make our life better, and that gives the impression that science should also be mission-driven. We should be driven by a sense of mission to help humanity. But yet, in your book, you portrayed also a scientific endeavor, almost like that of an artist, that's searching for beauty and looking at nature as a piece of art that we can appreciate. And oftentimes we make the most fundamental discovery, oftentimes driven by curiosity rather than utility, and by beauty and kind of artistic inspiration. So maybe you can communicate this idea a little bit more to the young audience.
Yes, well, science works on different timescales and with different intentions. People often want to produce specific results, to design a circuit, to design a computer, to design a product that people will enjoy and buy. That's very legitimate. It's a very important activity. However, that usually involves taking concepts that exist and putting them together maybe in slightly different ways, but not changing them, not really changing the framework. There's a longer term activity that you can't really easily predict where it's going to lead, which is to play with the concepts, to see what might be different, or especially to see how they might be more harmonious, how if there are gaps in our understanding, can we fill those in? And it's hard to predict the consequences of that, but historically, that kind of free thinking without focus on immediate applications has led to many, I would say most, of the most profound discoveries that in the long run have also practical consequences. We mentioned earlier the Maxwell equations.
Our cell phone works because we have Maxwell equations.
Well, all of modern technology is firmly based on the Maxwell equations, plus, of course, classical mechanics, which was originally designed or developed in its powerful form to understand, of all things, how little lights work around, move around the sky, and not most of the lights. Most of the lights move very nice. There's stars, but a few planets do funny things, and people wanted to understand that. They didn't
very
know.
Much driven by curiosity.
Very different, totally driven by curiosity, and driven by kind of obsession with how things almost are simple but not quite, and want to get it exactly right. And and then of course in the 20th century we had the triumph of quantum mechanics, which no one would have dreamed up by thinking about practical problems. It's just it requires fundamental revision of thinking, very counterintuitive. Students, when they learn quantum mechanics, have to kind of unlearn things that they thought they knew about how the world works and expand their imagination. I mean, I love quantum mechanics because it's the most mind-expanding thing that I know about. It's like art in that way. It's the best art. It's mind-expanding. It was driven by curiosity. How do things work? Well, finding out how things work pays off in the long run, because it gives you power and gives you not just aesthetic pleasure, but also the ability to do new things.
That's really wonderful. So, Frank, I love to read your scientific papers. I love to read your popular science books. Also like to read your Wall Street Journal columns. One thing that occurs to me is that you're extremely broad, your knowledge base, that you often talk about philosophy, poetry, art, and science. And within science, you not only work on high energy physics, which you originally focused on, but you were just talking about the beautiful work on anions, which relates to condensed matter physics, which is what I work on, but also on cosmology, on very big things, on very small things. But how do you get to there? I think the students generally like to know. But do you advise them to initially focus more, then become broad, or should they be broad and focused at the same time? Or what maybe your personal journey and what's your advice?
There are different scientists who have different styles who are quite successful. I think one thing that makes it less impossible to operate the way I do than it might seem is that although those subjects describe vastly different phenomena, and very different kinds of objects, the underlying mathematical description turns out to be remarkably uniform, because these deep concepts of symmetry and continuity, differential equations, topology, the mathematical techniques, especially in quantum mechanics, are so powerful and so broad that you can describe a lot of things once you have these tools. I mean, your question was more broad. How, I mean, it's not just physics.
Your personal journey,
My personal journey.
Were you
I never
initially broad and then focused, or were you first focused then
I was
broad,
very,
or you were always the same time?
I was very, very unfocused, then got focused, and then defocused again. So, you know, when I was a child, I knew.
You talk about philosophy.
I loved
to read.
mathematics, and even within philosophy, what I found most congenial actually was kind of mathematical logic and analyzing the arguments very rigorously. But I didn't really intend to become a physicist, much less a high energy physicist.
Really?
Even going into college, my intention was to study, to figure out how minds work.
Oh, really? Neuroscience?
Well, neuroscience, or some combination of neuroscience and computers science, and philosophy, to understand how minds work, really understand it, not to make mathematical models, sort of the sort of thing we talked about with maps, where you do computations and you have these objects that are mathematical symbols, but maps of molecules, and they actually reproduce, they are accurate maps of how molecules actually work. So I wanted to have something like that for brains, even maybe simple brain, maybe fly brains or rat brains, or but I quickly learned that the subject wasn't ready for that kind of treatment. Was not, and I wasn't really cut out for laboratory work, and I didn't have the patience. So I majored in mathematics just because I didn't know what I wanted to do. In undergraduate, and even I started graduate school in mathematics. I never really intended to study mathematics, so it was kind of irresponsible to do that. But I didn't know what I wanted to do. So I went to Princeton in the mathematics school, in graduate school. And then I wandered around for a couple of years, going to biology seminars and chemistry seminars and physics seminars, and looking for opportunities, really. And I was very fortunate to be in the right place at the right time, because at that time, in the early 1970s, was when some very powerful ideas about, technically you'll know these things, renormalization group, gauge theory, there's tremendous amounts of symmetry, were breaking through in the description of the world, and they were a very good match to the mathematics.
To your background,
to my background. So that's when I went all in. Then I had to focus, actually, do calculations. So I did, and of course it worked out very fortunately. And because it was this breakthrough in understanding the strong interaction, it had a lot of consequences that one could build on for unification of forces, calculation of new processes. I thought, well, okay, so now we've understood the strong interaction. Now let's understand all the interactions. It can't be that hard, much harder.
Pursuing Einstein's dream.
And then realization came. It wasn't very deep, but I think I was one of the first people to really emphasize it. That knowing how matter suddenly understanding how matter behaves in extreme conditions and that it's simple allows you to discuss what happened in the Big Bang in a much more rigorous and detailed way, because now you have the theory of the matter.
Right.
So you can compare guesses for what the early universe was like, the very early universe, to what the world really is. And so I got very involved in cosmology. And then eventually, but so that was a 10-year process. 10 years really. Then I went to Santa Barbara, to the new Institute for Theoretical Physics in Santa Barbara. I just was restless, I guess. So I went. I was not unhappy at Princeton, but this was new and exciting, so and better weather. So I went to Santa Barbara, and but there the dominant activity was condensed matter physics. And I soon discovered there were very interesting things going on there that again used the tools.
The same mathematics.
Well, the same mathematics and some of the same physics. Is that again symmetry, again quantum field theory, the kind of things that we had developed with great power in the world of elementary particles, but it was very striking to me that whereas the world of elementary particles is relatively paltry, there are only so many elementary particles and the experiments you can do are kind of restricted. You bang things into each other really hard and see what comes out. That's the basic experiment, and that's the only experiment. But in condensed matter, you can do all kinds of things, right? And there were some people I really liked and admired, Bob Schrieffer and Walter Kohn, and these giants of condensed matter physics happened to were at Santa Barbara, and so I got very much involved in that. That also turned out very well. So it was I didn't set out to be broad. It was kind of one thing after another, and they built. But one thing that's I think is true that is that I never let go of something. Once, I keep coming back to the things that I worked on before, and sort of it's like an ascending helix. So you keep coming back and using what you've learned in your journey to go higher.
That actually brings me to the next question. Actually, I didn't even know that you had an early interest in neuroscience.
Yeah, and I have continued interest in it.
So, but now that you're an accomplished physicist, right? Do you think that you can afford a little more time to think about both neuroscience and the brain science specifically?
I'm very tempted because, I've actually in recent years,
but also engage in a little bit more discussion about artificial intelligence.
Yeah, well, it's very striking to me that in recent years, the understanding of what are called neural nets has become much more powerful, much more mature. And is one of the leading approaches to hard problems in artificial intelligence. In this recent triumph of artificial intelligence to play the game Go very well, neural nets played a big role. And neural nets, I mean, as the name suggests, they're inspired by nets of neurons. So they kind of, at least in a caricature form, in a simplified form, they work the same, they use the same elements that are inside our heads. If you look at the theory of the neural nets, some of the most important ideas were contributed by physicists from statistical mechanics.
John Hopfield comes to mind.
Hopfield comes to mind, and Jeff Hinton. Some of the designs are things they're called Boltzmann machines.
They all named after physicists.
And in recent years, it's been there have been dynamical systems playing into this, systems of oscillators, and so it's really tempting, and. I think I may go back to that in a deeper way. In fact, in recent years, I've actually been doing some very nitty-gritty kind of work, partly coming out of the book, actually, on perception.
Yeah.
And especially,
you're writing a book.
No. I wrote the book. The book, this beautiful question book, in the chapters on Maxwell. And studying Maxwell, I learned that he spent a great deal of his time studying color perception.
Oh, he actually, even Schrödinger studied color.
And Schrödinger later studied color, and of course Newton made profound contributions to color theory, and Helmholtz, so some towering figures. Several of my heroes in physics had this interest, and so do I.
Wow.
So Maxwell's great contribution in color science was to realize that human vision is what's called trichromatic.
Right.
That it's, in a sense, three-dimensional. That you can synthesize, given three beams of different colors, you can mix them in different proportions and get any color. Any perceived color. Even though physically, the colors of the rainbow are completely different. Each one is different from the other physically. But to perception, you can mix several to get the same perception. So I got to thinking, it's a long story and maybe not so interesting how, but I got to thinking about the possibility of expanding perception to more than three colors by using some of the untapped resources of our minds. Because there are other animals, even modest animals like bees and pigeons, that have more dimensions of color. And modern technology allows you to process the signals that get to us in ways that can use the information that's coming in and translate it into a form we can understand. So I've been working on that, and I am, as we discussed, I'm very tempted to just make time to get serious about neural nets again. There's some of the work I've been doing recently on time crystals, which is I'm very pleased with, has brought me into contact with dynamical systems. So it's kind of, it's getting so close that it's hard to resist.
Now let me ask my last question, which may relate neuroscience to your book. So it looks like quite a remarkable phenomena that all great scientists, when they talk about, we know truth is kind of objective. You can do an experiment to test it. But the sense of beauty is somewhat subjective, right? But yet, among all leading scientists, we all share the same sense of beauty once they're kind of discovered.
Pretty much.
But my question is, how universal is that when you go beyond the ordinary human intelligence? We can, after some point, we can imagine artificial intelligence studying the law of nature, and we can very well imagine they may discover some law of nature, but would they, after they discover them, have the same sense of beauty as we do? Is it unique to human, or is it even more universal phenomena among intelligent beings?
I think I agree with you up to a point that most physicists, most of the time, agree on what's beautiful and what's not. Not always, though. Some people find complicated theories less compelling than others, even if they're very nice constructions. When you do one thing and then do another thing and then do another thing, and you've made a nice machine at the end. Some people say it's just, some people would react, well, it's just a whole bunch, a bag of tricks, whereas other people say it's a beautiful line of thought. And of course, the sense of beauty that comes into play in physics is not the complete sense of beauty that people have. People find beautiful landscapes, for instance, that don't particularly reflect any scientific beauty that we find in physics, or of course the beauty of the human body doesn't really have much to do with the kind of beauty that we perceive.
Maybe in the sense of symmetry. Maybe in the sense of
a little bit.
Yeah.
I don't think that takes you very far. But I think the essence of beauty, that if this is my theory. This is not, I don't think, a consensus in any way, or even anything that I've heard anyone else really say concisely. which is that I think the essence of beauty for physics is the idea that you can have a description of many things that is very compact. That you have this kind of
simplicity
data
and universality.
Simplicity. So I mean, simplicity is a very special thing. It means you can have a compact description that may be difficult to unfold, but it's unambiguous. You start with a very compact description, you unfold it, and you get something miraculous, and you get a description of the world. It's sort of like a fractal, right? The fractal is a very short computer program, but gives these elaborate, very complicated looking patterns. And I think most people find that beautiful, and I think that is very close to the core phenomena of beauty in science. You find that you get much more out than you put in.
So now, coming back to my question, if artificial intelligence discovers
I was building to that.
So
now for artificial intelligence, I think that'll still be the case. Of course, no, I mean, because it's artificial, you can design its taste, so to speak. You could make it not like that. But I think for an artificial intelligence to really be powerful, you would want to have it desire this kind of description that's compact and powerful. The thing about artificial intelligence, I mean, the ones we can kind of envisage, is that they will probably, well, they will certainly be much better at computation than humans. I mean, humans can partner up with computers, but if you didn't have to write programs and muck around, it was kind of complicated. If you could just do it, you would have a different perception of what's complicated and what's not. So the laws that you end up with might have a different emphasis. What an artificial intelligence would consider a compact description might be quite different from what a human considers a compact description. Of course, the physical world is the physical world. I think ultimately they have to agree on the results, but I think the way in which those things would be stated might be quite different.
So when do you think your book will be translated into Chinese?
Very soon. I think.
So we look forward to the days.
I should look in. I'll look into that. I'll ask. I can find.
So I think after our conversation today, the audience will be very interested in building up the anticipation.
So I will get that to you.
And we thank you for giving us this opportunity to share in advance of the translation.
The translation has been underway for
a beautiful book about a beautiful idea.
The translation has been underway for several months, so it should be near completion now.
Great.
All right.
Thank you very much. Okay, good.
Right. Bye.